Hi, everyone. Welcome back to the first webinar of today, Thursday. And we're talking about space again, obviously.
Greetings.
Obviously, we're talking about space.
Greetings, Earthlings.
Greetings, Earthlings. Okay. Bunch of people hanging out in the Q&A section already, even before we started. April says she's almost done with her space helmet. Yeah.
Oh, cool. I can't wait to see it, April.
Again, for those of you who were with us yesterday and we were talking about making space helmets like these, I would love if you took a picture and sent them in to events@delphian.org. I'm going to, let's see, I'm going to pull up that email again really quick. Hey, bear with me.
Also, too, I'd like to hear where everybody's from today. If you haven't tuned in before, let us know where you're from. I get excited when I hear from people all over the world. So exciting. Yeah. Hi.
There we go. Events@delphian.org.
Oh.
That is the email address to send your pictures of your completed amazing space helmets to, and I'm really looking forward to seeing them.
Hi, Aletta. Is that Aletta?
Yeah, there's a billion people saying hi, so we are going to have to just kind of plow on, because he pointed out to me, he said, James, there's like 60 slides that you have prepared today. I thought, oh no, if you were with me on Friday when we went for almost an hour, that was like 40 slides. So I have even more prepared today. So we're going to have to go quick.
Yeah, exciting stuff.
All right. There's people here from Oregon and New Jersey and California and Earth. Thanks, Cosmo.
Earth.
Cosmo says he's from Earth.
Cosmos from Earth.
He's not wrong. California, Tennessee, Manassas, Oregon.
Manassas! Is that Manassas, Colorado, I think? Yeah, probably.
I'm not familiar with another Manassas.
Yeah.
Venus. Hey, Logan. Logan's here from Venus. Portland, Clearwater. We got people from all over the place. Otis? Jamie's in Otis? They have the best bread in Otis.
Oh, awesome.
All right, we're talking about types of stars and their life cycles. And I say so cycle is something that happens over and over again, right? Like you wake up, you eat, you do a bunch of stuff, you go back to sleep, and then you wake up again. That's the cycle of the human day, right? So we are going to get into this. I'm going to show this picture a few times, and we're going to go over it a few times. So if you don't catch or capture everything from this the first time, don't worry about it. We're going to come back and we're going to look piece by piece and put this together. But here's the general basic life of a star. It starts with this cloud of gas and dust, just floating around in space, just chilling, having a good time. I say chilling because it's really cold. It's like negative hundreds of degrees Celsius, cold. But gravity likes to hang out. Gravity likes to have stuff hang out. It's like if you are in a room, Diego, if we're in a room and there's like 1,000 people just kind of scattered all over the entire room, you know, back when you could be in rooms with people. and there's going to be that one person that goes around that just kind of like, hey, no, come over here. And this is my friend Diego. Have you met Diego? Yeah, talk to Diego. Hey, Bill, come here. This is Diego. And people start clumping together. Gravity likes to have people hang out. It likes to have things hang out. And it's going to start bringing that cloud together.
Or like James when he's telling a Star Wars story. People will come around. People come around. Yeah. Some people come around. You get people that are there. They're very interested in it.
Like, ooh, James is talking about Star Wars again.
When I hear people talking about Star Wars, I gravitate towards it.
There we go. So it's going to either form into a small star or into a large star. Small star goes through this life and turns into a white dwarf. And a large star goes through this life, turns into either a neutron star or a black hole. If I'm going really quick for you, don't worry. Again, we're going to cover each of these things for a little bit, so you get to figure out the pieces and then see how the pieces fit together. Okay. So many people in the Q&A section. This is amazing. All right. Fallon asks, what's a protostar? Stick with us and we're going to find out. Yeah. What's a planetary nebula? Stick with us and we're going to find out. I understand I'm throwing words at you that you don't understand yet. But I wanted to give you the overall picture, and then we're going to go and learn and define and figure out what are each of these things. Okay.
And keep in mind, there's still a lot to learn. So
So much.
even though we have even top physicists around the world, this is the apparent evidence, but then they find stuff out all the time.
All the time. And I'm going to cover some of those recent discoveries here today. Yeah.
Let's get started.
Good. So whatever happens, it starts with this cloud of gas and dust. And I know it says protostars in there. We're going to find out what those are in just a second. Here's what some of those clouds of gas and dust look like. These are some actual pictures taken of stuff out in the universe. And these are called nebula. Nebula, these clouds of gas and dust, just kind of like floating through space. These things are light years across. These are huge, massive, massive. Many of our solar systems could fit in each of these pictures that we're about to look at. This is maybe the most beautiful of them all. It's called the Pillars of Creation. And you see there's like almost these fingers reaching out. Those fingers, they're clouds of gas and dust reaching. And in those, stars are being born. And okay, so these nebula have lots of hydrogen. Okay, now hydrogen is the simplest and most abundant element in our universe. Just keep this in mind. There's a ton of it out there. It's going to be really important later. Do we have a model of a hydrogen?
We have hydrogen. That's pretty much it.
Boop.
This is
there we go.
This would be your electron here, and then your proton in the middle.
One electron, one proton.
So we have
super
hydrogen.
simple. And if you don't know what those are, just what you need to know is that it's the simplest possible little atom in the universe. Okay.
Yeah.
All right. So here's some more nebulas. Okay. Here's the Bat Nebula. Isn't that cool? Now, these aren't the real colors that the human eye would see. Scientists have added the color in order to highlight certain things, but it looks amazing, right?
With certain telescopes, you can see different types of light.
Different types of light, yeah. Here's the Ring Nebula. That's so cool. Here's the Crab Nebula. Doesn't look like a crab, I guess. Maybe, kind of. I don't know. It looks amazing.
Crabby.
I mean, if they just called every single nebula the really cool nebula, it would get old quick.
Yeah.
That's why I'm not an astronomer. The Phoenix Nebula. That looks like a phoenix.
This one was new to me, and so when I saw this,
it looks like a movie
the
poster.
Phoenix Nebula is really cool.
I feel like we're about to go watch a movie, right?
Yeah, you see the fire.
Here's
spiraling.
just Nebula from Marvel. I had to throw that in there. Here's the Seahorse Nebula. Okay.
That does look like a seahorse.
It does, right?
See the head right there?
Yeah, there's the head. All right, so within a few 100,000 years, very, very quickly in space-time, that cloud starts to clump together and spin. Like I said, it doesn't like to just be spread out. Gravity wants stuff together. It wants it nice and close. And it starts to spin, and gravity presses the center into a sphere, and it starts to heat up. It starts to get really hot, like 2 million degrees. That's a protostar. So there's one of our first big words defined. And proto means early or first. Star means, big ball of burning gas in the sky. How does it burn? We're going to find out. This is not a real picture. This is an artist putting together what it might look like. But I really liked this one. It gives the right idea. You can see all the gas and stuff with a glowing thing in the middle. This is another artist picture of what it might look like as one of these early protostars starts to form. It's really messy on the outside, This is an actual picture, okay? You can see a glowing disc around the edge, and those are two stars forming, two protostars forming. So later in the life of these stars, this could be Tatooine. You could have, a planet orbiting two stars. That's not uncommon. Scientists think that more than half the stars of our galaxy, more than half of the star systems, are made of 2 or 3 or more stars. that a system with just one star like ours is less than half of the star systems out there. That's really cool.
Yeah.
Our closest star, or our closest neighboring star to our own, is actually a 3-star system, a trinary system. Trinary means there's 3 of them. This is an actual picture of an early trinary system, an early system with 3 stars. And you can see them forming. There's a big one on the outside, and then 1, 2 smaller ones on the inside.
Wow. Hot days if you're orbiting those.
Right. So these are 3 protostars, 1, 2, 3, but they're all orbiting around each other. That's going to be a star system that is going to have 3 suns and however many planets form out of that. Okay. So 10 million years later, and that core, that center bit, is more than 18 million degrees. We thought 2 million degrees was hot. Hold on to your socks. 18 million, here we come.
So to get a perspective, what is our sun's temp? Do you know?
I
can pull it up.
Yeah, let's Google that real quick. I know that the surface of our sun is like, I don't know, 5,000 degrees Celsius or something like that. But the core of our sun,
average temperature of our sun
let's
is,
see, that's
surface temperature is
about
5,000.
about 5,500. Okay.
Yeah, 5,500.
What about temperature of the core of our sun? This is, I didn't look this up. He's asking a really good question right here.
Temperature sun, Google. About 9,000 degrees.
Fahrenheit.
Oh,
that's the surface.
Sorry.
Google, tell us what we want.
Yeah.
Here's the glorious process of research.
Yeah.
Yeah.
Well, I'll have you continue on that, and I'll pull this.
Good.
stuff
Okay.
up.
Well, anyway, so I know that the core of our sun is at least 18 million degrees, because at 18 million degrees, there's enough heat and pressure that we can create thermonuclear fusion. Oh, big word alert. Big word alert. Thermonuclear fusion. We're going to find out what that means exactly. Okay. The core of our sun is about 15 million degrees Celsius. That's 27 million degrees Fahrenheit. Ha! Wait, 15 million degrees, 18 million degrees. All right, good. So I think that the degrees that I put here is Fahrenheit, because it needs to be that hot in order to create thermonuclear fusion. What does that mean? Thermo, having to do with heat. Do you have your thermos?
Thermos.
Okay.
This isn't a plug.
His kind of cup is from a brand called
Although
Thermos.
I do love this cup.
They call it thermos because thermo is having to do with heat. This keeps your coffee hot. Thank you. Nuclear, having to do with the nucleus or the center of an atom. Okay, good. And fusion, joining together. So thermonuclear fusion, using heat to join together atoms. Good?
Yeah.
All right. Got it, Diego?
Got it.
Great. All right. So remember all that hydrogen that we talked about earlier? Now it's important, because what's happening is it's going to take 4 hydrogen atoms.
Here's 2.
And it's going to combine them into 1 helium atom. So let's show that here real quick. You got,
there's 2 and another 2.
And these things are like flying around, and they don't like getting very close, but there's so much heat. There's so much pressure. You know, you've got a room full of people that they're trying to keep their distance from each other. Like, I don't want to talk to this guy. I don't know. He seems weird. But the room is so crowded, you have to get close to people. And then just to be polite, you're going to be like, hey, I'm James.
Hi, James.
Hey, do you like Star Wars?
Yeah, I do. I love
Me
Star Wars.
too! Boop. Great. Those atoms just fused.
Did we just become best friends?
Yup. So these 4 atoms will fuse into 1 atom. And that atom is called helium. So here is a drawing of 4 atoms becoming 1 atom. And you can see 1, 2, 3, 4 hydrogen, and they go boop. And there's this heat and explosion and energy coming off, and then you have a helium atom. And what comes off of that is a bit of energy in the form of heat and light, and this thing called a neutrino, which is just kind of junk in the process. We're not going to talk about neutrinos right now. Here's another picture of 4 atoms fusing into a new atom. Yeah.
Where's my symbols?
So we're not talking about Adam Driver or anything. We're talking about atom, A-T-O-M, instead of A-D-A-M. Okay, so here is just a little illustration showing atoms crashing into each other, and you can see there's like this burst of light and kind of heat that comes from that. This isn't really scientifically accurate, but it shows the concept, and that's why I wanted to put it here. 600 million tons of hydrogen combine every second in the core of our star and most other stars. This creates 596 million tons of helium.
Wow.
Okay, now do the math on that, Diego, and tell me, actually, you guys, tell me, what's missing? 600 million
minus 596 is...
What's missing there? Here we go. 4, yeah. Milo is the first one. And here's a billion people replying with 4. There's 4 million tons
missing stuff.
Missing from that process. What happens to it? Where does that 4 million go? What does that 4 million turn into? I want to
wise questions.
See your. Kanan says easy math. Yes, it is easy math, which is why I was able to do it. Those of you that were on Sam's fractions webinar the other day, he asked me a question, and I didn't get it right because I was too busy eating cake. That's a true story.
Because you guys are dividing up the cake?
Right. Yeah. So what happens is the hydrogen turns into helium. But as I said a couple of slides ago, hi, Adam, some of that stuff turns into energy in the form of light and heat. 4 million tons of heat and energy generated every second from the core of our star.
That's a lot of energy.
That's a lot of energy, and that energy pushes out, right? We've all seen a movie where there's an explosion and our hero gets like pushed away, away from the explosion. There's that outward force from heat and light pushing out.
Solar wind?
Yeah. So the fusion is pushing out, but gravity, that really annoying person in the room, like, come here, no, come here. We're talking about Star Wars, come here. That gravity is constantly pushing in on the star, trying to crush that star inwards. Like, we're going to be really good friends. And the fusion is trying to push out. And every star for a while is going to find this balance where the fusion pushing out equals the gravity pushing in. Yeah. If I was to push this way and you were to push this way, it stays right in the middle. You have a nice stable star. Okay. All right.
It's like a party where you have even a good party, you still have people coming out and you have people coming in.
Mm-hmm. And it's just a nice balance, right? Mm-hmm. Okay, so we're going to go back to this picture for the first of many times. So we now have either a small star or a large star. So what we've covered up to this point, the cloud has condensed into a protostar. That protostar has brought in more and more until its core got hot enough to start that thermonuclear fusion. Poof, you got a star. Now, we're going to follow the life of a small or medium-sized star for a little bit because that's what ours is. That's what our sun is like. And that's really good. I'll explain why in a few minutes. Mm-hmm. So a small star is going to have a longer life than a large star. The bigger the star, the quicker it's going to die. And so our sun is going to last about 10 billion years. We're right in the middle of that. We're about 4.5 billion years into its life.
That's a long time.
Yeah, don't worry. You have plenty of time to, watch all the Star Wars movies again. Plenty of time, okay? And there's smaller types of stars called red dwarfs that are much, much smaller than our own star. They still have thermonuclear fusion going on, but they're going to last for trillions of years, some of them. I mean, the universe is only 14.5 billion years old. Scientists don't know what the end of the life of a red dwarf looks like because the universe hasn't been around long enough for them to die for them to run out of that fuel. They're burning their fuel very slowly. You know, it's like if we got plates of ice cream, right? Plates, bowls, and you had a big bowl and I had an even bigger bowl, right? And I'm like, oh no, 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 I'm eating super quick. I'm this blue-white super giant, which is going to eat through that ice cream so quick. I'm going to eat through it in a million years. And then it's gone. You see that you don't have a lot, and you're just going to take little bites. And you're going to be around for trillions of years eating that ice cream. Mint. Okay, so the smaller it is, the longer it lasts. The bigger it is, the quicker it goes through everything and explodes. Whee! Okay. Oh, Fallon asks, what is a solar mass? Okay, that's a handy unit of measurement. Mass is how much matter there is on something. You could roughly call it how heavy it is. Okay.
How much stuff it has.
Yeah. Like I am more massive. I have more mass than Diego. I weigh more than him. Okay. It's probably true. And so the mass of our sun, exactly how heavy our sun is, they call that one solar mass. So this blue-white supergiant over here, it's as heavy as 150 of our suns.
150 stars.
Wow. 150 of our suns is how heavy that guy is. Okay. So when the sun runs out of hydrogen to turn into helium, that core starts to shrink, right? So all that energy and stuff was pushing out, and that was keeping the core bigger, but it's running out of hydrogen. It's running out of fuel. It's running out of food, and it starts to, and gravity never went away. It's always pushing that core in. Well, that creates more heat and pressure, okay? So it's now making less heat from fusing hydrogen into helium, and it's making heat because it's just getting squished. Like when you get too many people in an elevator to get together and the temperature starts to go up. The core now reaches temperatures of more than 100 million degrees. That's a lot of degrees. That's really hot. And so the sun says, all right, I'm running out of helium. I'm running out of hydrogen to turn into helium. Now for my next trick, I'm going to take that helium. I got plenty of that now. I'm going to turn that into carbon. I'm going to fuse that helium together into carbon. So
3 heliums.
So here's 3 heliums
into a carbon. Bam! 3 heliums.
So each of these 4 hydrogen had combined into a helium. And now it's going to take 3 helium, and they're going to fuse together, and they're going to form carbon. And going back to the slides. All right, so here's 3 helium. They form into carbon. And again, that generates heat and energy and light. And you see these photons. Photons are what light are made of.
Then what does carbon turn into?
Yes, we're going to talk about that in a little bit. So a thing like our star, it has enough heat and pressure that it can turn helium into carbon. And that little trick is going to buy it another 100 million years. Not a lot of time, but some time. And so it's going to be fusing that helium into carbon, but it comes at a cost. The star is going to start to, that core gets smaller and smaller, but it's losing mass. It's losing matter. And the gravity starts to get a little bit weaker because it's losing that stuff. So the star itself, the outside of the star starts to swell, and you can see it here. It gets bigger and it gets bigger. And this is an illustration of what our sun is going to do in about like 4 billion years. Don't worry about it, right? It's a long time out. The surface gets cooler and cooler. The star itself, the outside of it gets bigger and bigger. And near the end of it, so this is an actual sequence of pictures. This is real. As with anything that starts to run out of fuel, if you've ever been in a car that's running out of gas or something like that, it starts to go pop, put, put. It's like running smoothly. And there's like put, put, put. And it's kind of jerking and jumping. And it's not like it's burning fuel normally. And then there's like a burst of energy. And then it cools down. And there's a burst of energy.
It's not steady power.
Yeah, it's hiccuping. Or it's like a cat trying to hawk up a hairball. And when that happens, it starts to push out the outer layers of that star start to get pushed away. And this is an actual picture of that happening. And that'll happen many times. It'll start to lose the outer layer, and then the next layer, and the next layer. And it starts to spread out and to form this like cloud of gas and dust, which sounds kind of familiar. So someone asks, is this a supernova? Not yet. This is called a nova. A nova is when a star suddenly gets brighter and then dims back down. We're going to talk about supernovas in just a little bit. This is a normal nova, or just a nova. Here's and then so you see here's the outer layers of that sun. It's been pushed out and pushed away, and it's going to turn into this floating cloud of gas and dust. And all that's left in the middle is this little guy right here. It's called a white dwarf. And a white dwarf is, I mean, some of them are just about the size of the Earth. It's very small compared to the size of the original star, but it is 300 times more massive, 300 times heavier.
300,000 times on the slide.
What'd I say?
300 times.
300,000 times more massive than the Earth. Same size of the Earth, but much, 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 much heavier. There's way more. There's 300,000 times more stuff crammed into the same place.
The physics on that just.
Oh man, just
yeah.
There's no longer fusion happening. There's no helium being fused into carbon. There's no more hydrogen fusing into helium in there. None of that's happening anymore. All that glow, all the light, all the heat that's going to come from a white dwarf is just, it's like you had an iron and you were ironing stuff and then you unplug the iron. And it takes a while for the iron to cool off. That's what's happening here. It's just cooling off. And it's going to cool off for billions of years. It takes a long time for that much stuff to cool off.
That's a long time.
All right. What would happen if our sun died? Julian asked. Well, that's basically what we just went over here is the life of our sun. Okay.
That's what astrophysicists are doing all the time. They're looking at these
studying.
things.
Yeah.
They're looking at the beauty of the universe and trying to figure out what's happening to those other stars to find out what would happen to our star.
Exactly.
Given enough time.
So in about, 3.5, 4 billion years, our sun is going to start to swell in size like this. The core will get smaller and smaller. The outside will get bigger and bigger. And then eventually it'll start to puff out those outer layers. They'll go flying off and our sun will turn into a white dwarf. That's a long time from now. Very long time from now. All right, so AG asking the right question here. What if the white dwarf cooled off? What would it become? Well, scientists have a pretty good idea of what that's going to be, and they call that idea a black dwarf. And they don't exist yet because the universe hasn't been around long enough. We need tens or hundreds of billions of years for this white dwarf to cool off enough that it loses the light, loses the heat, and it would just become this floating ball of cool gas. Not hot enough to create light, not hot enough to create heat, or at least not a lot. And so it would look black. It wouldn't emit any light, so it would look black. Not a black hole. Those are very different. We're going to talk about those soon. So theoretically, we know about them, but we haven't seen any, and we don't think they exist yet because the universe isn't old enough. So Chris asks, after the sun is gone, will the planets drift away? The planets, unfortunately, will probably be destroyed in that process. As the sun gets bigger and bigger, it'll probably swallow up. It'll get big enough that it's bigger than the orbit of Mercury, maybe bigger than the orbit of Venus. maybe bigger than the orbit of Earth, maybe. But that part where it kind of puffs out like that, that's probably going to destroy the rest of the planets. But again, I'm not trying to make you all like sad or upset or like, we're all going to die. It's billions and billions of years from now. This is very distant future stuff. All right. So we're going to move on. So that's the life of a small or medium-sized star, okay? It turns into a small star. As it starts to run out of fuel, it starts to swell. It turns into a red giant. The outer layers puff away and become a planetary nebula. Like a nebula, just, big ball of gas and dust floating through space. And the core turns into a white dwarf. So what about a big star? What about when it was forming, it pulled in so much stuff. It made so many friends in that room. It turned into a huge star, many times bigger than our own. Well, that is able to do some really cool tricks. So when our sun runs out of helium, it runs out of hydrogen. It starts to take that hydrogen and form it. Hydrogen into helium. It takes the helium and it forms it into carbon. Well, the star's bigger than us. It can get more heat, more pressure on the inside, and it can not only turn helium into carbon, it can then turn carbon into neon, and it can take neon and push the neon atoms together to form oxygen. That's really important. And then the oxygen can form into silicon, like the stuff that we have in our microchips. And then the silicon can form into iron, like the stuff that our buildings and bridges are made of. And then the iron can't fuse. There's not enough going on in there to fuse the iron. So that's not. And that's where that process kind of ends in this.
With the iron fusing to itself.
Right. So the iron fuses to itself, but that's not creating energy. So it's starting to, well, you see a problem there. It's eventually going to run out of cool tricks to do. But it does all this way quicker than our sun. Our sun is going at a nice, controlled, easy rate. It's only burning like 600 million tons of hydrogen per second. A nice, easy, small diet.
Our sun is cruising.
It's cruising, man. It's just taking it easy.
Relaxed.
These giant stars and these super giant stars are like, let's do it all. Let's do it all now. Come on, guys. It's like, when Diego has 2 cups of coffee in the morning, he's just like, woo! Or me every day. So it burns through that stuff super duper quick. And what did I say next? Great. So at the end, when it's done with all that energy, like when I run out of coffee and I'm just like, okay, now I'm really tired. In less than half a second, the core of that star shrinks from the size of the Earth to the size of Manhattan. Wow. That quick. Can you imagine? Diego, can you imagine just
things, the mysteries of the universe.
It is incredible, the forces that are working in our universe. All right. Well, when that happens, again, when stuff crunches together, it creates heat and pressure. And when you take something the size of Earth and you make it the size of Manhattan in half a second, it creates a lot of energy. That, my friends, is a supernova. Someone asked earlier, that's a supernova, okay? Here is, I hope this comes through and it's not too choppy for you guys, but even if it doesn't come through clearly, I hope that you can see there's a normal star and then it just explodes. Bam, it's gone. That quick. And that turns into an even bigger nebula like this. So our sun at the end of its life, it's got these nice, comfortable little hiccups. The outer layers of its, yes, it's going to destroy the planets, but it's not super, super, super violent. This is super violent. Oh, man, look at that.
This is supernova.
That's a supernova. Well, a long time after a supernova. What's left over? Here's another picture. I mean, you can see the explosion that happened there, right?
Are these filters or real? What are we?
Scientists have added color to it so we can see everything that's going on. But yeah,
some of the different light types.
And there's the Crab Nebula. We looked at that earlier. You're like, wait, I thought that stars came from nebula. And then the stars turn into nebula? Yes and yes. What's my next slide?
The circle of life.
Oh, yeah, dude, it's the circle of life. This is a brand new picture. This was published last Friday. This picture is less than a week old.
It's beautiful.
This is from Hubble. The Hubble telescope took this, and you can see the remnants of 2 supernovae. Here's this one. This is a much older supernova. You can see it's more spread out, and it's covered more space, and it's starting to drift a little bit. This is a newer supernova, and you can still see, like in the middle, that's where the star would have been, and it's puffing out.
Wow.
Isn't this incredible?
This is amazing.
It's so cool.
The chaos of the universe.
Yeah. Lorna says, each country needs to build a giant spaceship in about 3 billion years. Yeah. Yeah,
Agreed.
Good point. Good point.
Agreed. I think a little sooner, but agreed.
Yeah. Let's see. So Chris says, are there supernovas that can bend a bit of space? Yeah. So the energy of that supernova is so intense that the fabric of space and time literally is like...
Even our own sun is bending space-time.
Yeah.
Anything with mass bends space-time to a degree.
But just to keep it very simple and stuff like that, yep, it bends space-time. That's how intense that explosion is.
Maybe we should talk about space-time, or are we good?
We're going to run out of time and space unless we bend it the right way. So I think we need to move on.
Let's keep bending.
Amelia says, do a black hole. All right. It's coming up, Amelia. Don't worry. So when stars die, they form nebula. When stars are made, they're made out of nebula. But what happened inside that star while it was alive, Diego, especially that supermassive star? What was being formed in the middle? We got carbon, silicon, oxygen, iron. Wait, these are really important things, right?
Yeah, they sound like stuff I had in my vitamins this morning.
This cup is made out of these very things that we were talking about. So it takes the center of a supermassive star to form these elements, and then they explode, and then new stars are born from the remnants of those old stars that exploded. So the first stars in the universe would have been made of just hydrogen. Yeah. And they would have been supermassive. And remember what we learned a few minutes ago, the bigger the star is, the quicker it burns through its stuff. Some of them only last 1 million years. So it would have burned through that stuff and made a bunch of helium and carbon and oxygen and silicon and iron and all this other stuff, and then exploded and taken those ingredients and just scattered them all over the universe. And then those clouds condensed into new stars, and they would have formed stars, and those stars would have done the same thing and exploded and scattered. So all these more different, complex, heavier, important molecules get formed into these and scattered, and it happens over and over again until you get a nice calm star like ours. And then we get, so every atom in your body, Diego.
All of them. The laptop.
Lorna and Shanna and Milo and everyone else tuning in, every atom in your body came from the center of a dying star. That's so cool.
That's an amazing. There's some cool songs with those in the lyrics.
Yeah.
We're all stars.
Yep.
We're all superstars.
So what's left after that massive explosion? Well, most of that star just gets blasted off into space to create new stars. Thank you, dying stars. What's left? As I said, that core collapsed from the size of the Earth to the size of Manhattan. And we're left with this gorgeous thing called a neutron star. And it's about the size of Manhattan. There's a picture of Manhattan on the right. And there's my favorite pizza place and my favorite deli.
Yeah, we were just there at Saturday Night Live.
Yeah. Here's another artist drawing. That last one is just an artist drawing what he thinks neutron star would look like. Here's another idea. 1 teaspoon of matter from that neutron star weighs 100 billion tons.
So the volume of a teaspoon, about yay.
100 billion tons. That's super heavy.
That's gonna.
And there's
blow
some
up space
crazy stuff happening with the physics around this star. You can see these jets of light shooting off the north and south poles of that star. Yeah, that is maybe not visible light, but it's like X-ray light. And it shoots off these super bright beams of high energy into space. Here's another artist drawing of the remnants of a supernova and that neutron star in the center shooting off those jets of extreme energy. There's another one.
There's so many particles going through space all the time. I've even heard astronauts say when they're outside, when they're in their spacecraft, as they're going to sleep, they see these traces of particles going through by their eye.
Yeah.
Their eyes are closed, but they'll see these cosmic particles go by.
Yeah.
It's a really strange phenomenon for astronauts.
I'm going to peek here real quick.
Sure.
How much do I have left in my slideshow?
Oh
no. Okay.
10 slides.
I'm speeding up. We have 3 minutes left and we have to end on time today because the next webinar that's coming at 10:15, Becca's talking about art history, and we are moving our entire setup to a different place. And I need time to do that, but I really hope you tune in at 10:15 to see where we went and what we're doing. This is a real picture. This is a real picture with some added color just to show what's going on. That is a neutron star in this, you can see some gas and clouds and stuff in the way there.
Beautiful.
Oh, we have to skip that. Okay, so what if the core, what if the center of that exploding star was even more massive than the one that formed a neutron star? What happened if you had more mass, more gravity, more mass, more gravity? That, my friends, will form a black hole. The gravity is now so intense, it's even more than this thing where it weighs 1 billion tons. 1 teaspoon would weigh 1 billion tons. Even heavier than that, black hole. Light gets too close to it and light gets sucked in. Light does not go out. That is how heavy the gravity is in a black hole. Here is what an artist thought that a black hole might look like. I think this is a pretty good guess. Mm-hmm. That light that you can see around the edges, that light is created from the energy of matter getting sucked into the black hole. As it gets sucked into the black hole, it heats up and it speeds up because it starts going really quick and it's bumping into other matter and it heats up and it creates energy and light. But so that light that you see is from the outside of the black hole and then this black center inside. This is a real picture. That last one, that was an artist putting together what he thought it might look like. This is a real picture of a black hole. This just came out like last year. It's super distant from us. Don't worry, we're totally safe. Mm-hmm. But that's a real picture. The science behind what it took to get that picture and 20,000 years of human evolution to get that photograph, an amazing story. Now, scientists knew that there were stars that were even bigger than those that create neutron stars and black holes. And they knew that there would be an explosion so powerful that it would even blow apart that core. There would be no neutron star because the core would get completely blasted away as well. So they took this picture back in 2006. They found the supernova that they called SN supernova 2006 GY. And it was 100 times more powerful than your normal supernova.
Whoa.
And they're pretty sure that there was nothing left behind after that, just that expanding cloud of dust and, some iron and oxygen and stuff like that.
This is in another galaxy, or this is
another galaxy. This is, oh, yeah.
Yeah, okay.
This is a long time ago in a galaxy far, far away.
There it
Literally. Okay. So I knew we were going to run out of time. Here is that first picture I put up. We start with that cloud of gas and dust. It forms into a small star, which at the end of its life swells into a red giant, puffs out into a planetary nebula, and we're left with a white dwarf. Or it forms into a large star, forms a red supergiant as it swells near the end of its life, but it dies a lot quicker, goes supernova, and turns into a neutron star or a black hole. And then that supernova or that planetary nebula is this expanding ball of gas and dust, which more stars will form out of. It's poetic. Oh my gosh. Okay. How many stars in the galaxy? 100 to 300 billion. There's 1 to 200 billion galaxies in the universe. I tried to do the math on how many stars there were, and my calculator just said it's like a lot.
A lot.
We're out of time. I gotta skip some stuff. I'm so sorry, everyone. Thank you for joining us today. I'm gonna end off really soon so I can take this whole setup and move it to a different place. I hope you join us at 10:15 for our next one. And Diego and I will be back tomorrow afternoon at 2:30 talking about the search for alien planets.
Ooh.
Yeah.
Gotta see that.
Space helmets on.
Space helmets on.
All right. Bye, everyone.
Bye.